Hi, I'm Abby, and this is lab number 4, circuits. In this lab, we visualize the impact of resistors through the loop rule and current conservation. We examine series and parallel circuits, predict potential difference in the circuits and the changes in a circuit as time passes, and we explore time-dependent voltage and current in a DC current. Our results showed that the current and voltage values given by the model match the predicted calculated values, and in an RC circuit, the magnitude of current is time-dependent. The fundamental physics principles in this lab are as follows. The node rule, which states that the current coming into a node is equivalent to the current coming out of the node, and this utilizes the conservation of current. The loop rule, which states that the change in electric potential round trip in a circuit is equivalent to 0, and this utilizes the conservation of charge and energy. Ohm's law, which states that the change in electric potential is equivalent to current times resistance. The fact that capacitors store electrical energy, and the connections in series versus in parallel are different. In series means that the current in both resistors is identical, and in parallel, it means that the voltage across each resistor is the same. In the experiment, the system was the circuit and the surroundings was everything else. We assumed that the resistance of wires is negligible, and the resistance of an ammeter is also negligible. In the first part of the experiment, we used two 1.5 volt batteries, 2 ammeters, 2 resistors, which were 47 and 100 ohms each. In part 2 of the experiment, we used a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 200 microfarad capacitor. In part 1 of the experiment, we had a simple circuit with two 1.5 volt batteries, and the first circuit made will have a current of 0.2 amps, as seen with these. And here is the calculation for that. If the ammeter was read when inserted backwards, it would read that the current is negative 0.02 amps. Next, we replaced the ammeter by a voltmeter. The current read 0 amps because the circuit was open, and the voltmeter has such a high resistance that there is only an extremely small current running that the ammeter cannot measure it. The voltmeter read that the electric potential difference was 3 volts. There is no current, so there is no potential difference for the resistors and only the batteries, which has a total potential difference of 3 volts, or 1.5 volts per battery. And here are the calculations for potential differences between points, and this is the approximate graph of what it looks like for each of the points. The sum of potential differences total out to be 0, which is correct. When connecting the voltmeter across the 100 ohm resistor again, the ammeter reading is now 0.02 amps. When I replaced the voltmeter with an ammeter in parallel with the 100 ohm resistor, what happened to the current through the other ammeter and why? So, the ammeter reading increased to 0.06 amps, and this is because the parallel series avoids the 100 ohm resistor. And here are the calculations for potential differences of the following circuit elements. We have the resistance of the 47 ohm resistor, the 100 ohm resistor, the resistance of the wire, and the resistance of the ammeter, which both come out to 0 because that was one of our assumptions. Here are my initial recordings and observations from part 2 of the experiment. When the battery capacitor and 10 ohm light bulb were connected in series, the light starts bright and then became dimmer. When the battery and capacitor disconnected, the light started bright and then became dimmer again. When the battery and capacitor were connected with a 10 ohm light bulb, the time for capacitor to charge the light bulb was 8.9 seconds, and for it to discharge the light bulb, it was 9.4 seconds. When the battery and capacitor were connected with a 20 ohm light bulb, the time for the capacitor to charge the light bulb was around 18.3 seconds, and for discharge, it was 18.5 seconds. Here's the time-dependent voltage across the discharging capacitor for the RC circuit. RC is called the time constant of the circuit, and this is the time at which the voltage difference has dropped to 1 over E of its original value. This was the predicted time, 6 seconds, and this was the actual. So we took the negative slope, negative 1 over RC, which is this right here, and it came out to 6 seconds, which was equivalent to our prediction. A similarity between the calculations and experiment was that the calculated predictions aligned with the experimental model since the online experiment was used. A possible source of error could have been that since I used my phone timer to record how long it took for the capacitors to charge and discharge the light bulb, it may have been slightly incorrect for the timing. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated one? And what's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So, the ammeter would have had resistance, and this would have caused the current to be lower. A real ammeter might also give a more accurate reading depending on how small it can measure. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. This ideal model would be able to have the capacitor reach full charge immediately. And this is not realistic in an actual model due to the small resistance that exists between batteries and wires. In conclusion, we can study the conservation of energy in circuits through computational simulations and models, and the node and loop rules are important for calculating measurements across circuits.